Greetings YouTube. I'm the retro old guy, and today I'm following up on my previous video of the Commodore speed test in which I simulated numerous coin flips. I'll be showing you both the basic and assembly language versions and how they've been optimized for speed and efficiency. First, a little background on this program. Way back in my college days in the early 80s, I was given an assignment to create a program that simulated 1,000 coin flips and would compute the percentage of each run, which with a coin flip is always going to be near 50-50. Alright, the assignment was done in Fortran, I believe, on a Digital Equipment Corporation VAX mainframe. Alright, but since I had my own Commodore 64, I went ahead and modeled the program on my 64 in BASIC to get a working routine for which I then translated to Fortran. While I was doing this, I had shown this to my buddy who owned a Osborne CPM computer. Now an Osborne computer runs at twice the speed of a Commodore, so of course his program would finish in half the time mine did. And so this eventually became a competition to see who could optimize the routine for maximum speed and efficiency. This resulted in 4 evolutions of the program. Of course, in the end, I won when I created the assembly language version because he never learned how to program assembly for his Osborne. Alright, so let's get right to the evolution of this very simple program. Here is version 1 of the basic routine. This is roughly what I turned in for my assignment, and it was good enough to get the credit. But let's do a quick walkthrough of the code anyway. Alright, first we set the timer here to 0, so the computer is going to be our stopwatch. Then I set up a nested for next loop here, which is 10 loops of 1,000 iterations apiece, which gives us a total of 10,000 iterations. Now I used the nested loops so that after each 1,000 iterations I could update the screen. This does add more time to the overall runtime of the program, but it's negligible, and besides I wanted to be able to track the progress. And when complete, we grab the elapsed time and go on to display the results on the screen. Now let's take a look at the 3 important lines of code. This is where the magic happens and also where all the optimization takes place. First, we generate a random number. Now a coin flip only has 2 choices, so it's naturally going to just be between 1 and 2, and it will be assigned to x. If x equals 1, then we increment heads by 1, and if x equals 2, then we increment tails by 1. This is the textbook way of doing it. It was simple and straightforward, and it's how I did it for my Fortran assignment. Now when we run this version on the Commodore 64, it took 3 minutes and 3 seconds to run. On to the next evolution. The first optimization here was to remove the second if-then statement and use a goto to jump over the t equals t plus 1 statement when x equaled 1, or heads. This reduced the number of instructions the program has to execute, as it now doesn't have to evaluate x twice in each iteration. This is essentially just emulating an if-else statement, but Commodore 64 BASIC doesn't have an else statement, so we have to make use with a goto. So now the code looks like this, and you can see it's getting smaller. When run on the Commodore 64, we now have 2 minutes 39 seconds to run. When compared to version 1, that is a 13% increase in speed and cuts 24 seconds from the runtime. Any questions so far? Anybody? No questions? Good. Okay, moving on. As we studied the problem some more, we realized that a coin flip has only 2 possible outcomes, heads or tails. So it's only necessary to count heads in the loop, or tails if you prefer, but I'm using heads for my purposes. So tails is just a mathematical problem to be computed at the completion of each 1,000 iteration loop. So the goto is removed, and t is now computed as it exits the inner loop as our total number of flips, which is c, minus heads, which is h. This reduces the total number of executed instructions to half, leaving us with the smaller, more efficient routine. Getting back to the 64, this routine runs in 2 minutes 19 seconds, which is 13% faster than the previous version and saves us another 20 seconds. There is one final optimization that can be done to increase the speed and efficiency of our simple basic program. So let's consider the random number generation. The random number on the Commodore 64 returns a floating point number between 0 and 1. So we can remove the int function and just test to see if the random number is greater than half, which will be 0.5 in this case, and that will evaluate to one of two outcomes. So the random number generator and the increment of heads, which is h in our case, can be combined into a single if-then statement to eliminate the int, the multiplication, and the addition that was necessary to give us an integer number between 1 and 2. And again, we are reducing the number of instructions that have to be executed with each iteration. So here is our fully optimized routine. When we run it on the 64, it takes 1 minute 25 seconds to complete. That's 39% faster than the previous version, which was 3, and saves us an additional 54 seconds in runtime. Here is a chart showing the runtimes of each and the speed increases. The final version runs 54% faster than the original and saves 124 seconds in runtime. I think you can see now why us old-timers were always looking to optimize our code, both to reduce memory and reduce the runtime. Today's computers are so fast and have so much memory that optimization or efficiency in coding is hardly even necessary. Next up is the assembly routine. There's only one assembly version created and it works exactly the same way as the optimized basic routine works. So I'm just going to do a quick overview of the code for you. The assembly routine is 59 bytes long and is loaded by poking the instructions into the memory of the tape buffer of the Commodore 64. The tape buffer, if you remember, is pretty much unused unless you're actually loading stuff from tape. When called, it will perform 100,000 iterations, then return to basic where the heads and tails totals will be tallied and the screen updated. Now I use basic for updating the screen because it was more convenient. Alright, let's do a quick overview without going into a deep dive of the 6502 machine language. Alright, we need a quick explanation of how we're generating random numbers here. The Commodore 64 can utilize the SID chip's voice 3 noise waveform as a random number generator. It's being used essentially as a white noise generator. It only needs to be turned on once and it will generate random numbers concurrently and separately from your program. This is extremely efficient and much faster than the built-in kernel random number generator. I read about this method in a Compute magazine way back in the day, and although I don't still have the magazine, I did manage to find the article online, so I'll put a link below. Anyway, these 5 instructions do the equivalent of poking numbers into the SID voice register here, which are shown in red. Now that random numbers are being generated, we move on to the body of the routine, which starts at decimal 842. First we zero 2 bytes, hex FB and hex FC. That's decimal 251 and 252. This is where the total for heads will be stored. It's an 8-bit number, so the max value is 65535. Remember these addresses for later. Then we initialize the first loop, which will be 2 iterations. Next we initialize the second and third loop with 200 and 250 iterations respectively. If you're doing the math, that's 2 times 200 times 250 equals 100,000 iterations. Now here is the really efficient part. The SID chip that we turned on earlier is continuously spraying different numbers into this address. So all we need to do to get a random number is read the address. If our random number is less than 122, we skip to next. If it's greater than or equal to 122, then we add 1 to the storage location for heads. Then we decrement the third loop counter by 1. If the counter has not reached 0, then repeat by jumping back up and get the next random number. If it is 0, then we decrement the second loop counter by 1. If it hasn't reached 0, then we repeat by jumping back to the beginning of the third loop. If it is 0, then we decrement the first loop counter by 1. If it hasn't reached 0, then repeat by jumping to the beginning of the second loop. And finally, if we're finished, then we return back to basic. Here's the basic routine. Line 10 will turn on the SID chip for use as the random number generator. Lines 20 and 30 will initialize variables and set the timer to 0. 40 will start our for next loop, which will be 10 iterations. And 50 starts the ML routine, which will do 100,000 iterations. So repeated 10 times in the for next loop, that will be 1 million iterations total. When the ML routine is complete, it returns to basic, and line 60 will increment the counter. Now line 70 will get the total for heads by peeking addresses 251 and 252, which, if you remember, these 2 bytes are used for storing the count for heads. Once that's obtained, then it will do the appropriate multiplication and addition for the bytes in order to get a decimal number. Then we go on to update the display and continue on until the loop is complete and we read the end time. Alright, well, that concludes the Commodore portion of the speed test. Now I want to show you a more modern day implementation of this program. This is an Objective-C program created with Xcode and is currently running on an iMac Pro with a 3.2 GHz Intel processor. It simulates both a coin flip and a dice roll and works using the same method used in the 64 version. And you can see it's got counters for the iteration, timer, plus a small table to keep track of all the results. The first run will do 1 million here, and you can see it took just a little over 1/10 of a second to do 1 million iterations, and that's for both a coin flip and dice roll simulations. So next, let's change the number to 10 million iterations and see how long this takes. You can see it only took about a half a second. So we're at 10 million iterations and we still have not even reached a second yet. So we'll max this out here and do 100 million iterations. Okay, this is actually taking some visible time here. And you can see 4.9 seconds, or just under 5 seconds, to do 100 million iterations. And that is the power of modern computers. Of course, your time may vary depending on what else you have running on the system or your processor. Well, this concludes the video. I hope you found it educational. And if anyone can create a faster way to do this, I would very much like to know. This has been the Retro Old Guy, signing off.